of time. It has a function of time. So it's still a function right now. It's still a function. So which means the other unknown is time. Is time. So in this case, what can we do? Yuxing? It seems like you have the answer. What can we do?
Maybe we have to know when exactly was the scanner passed by the point.
How to know that?
How?
Two unknowns, two equations. Two unknowns, two equations. So you should be able to solve that by the equation that you have right now. Two unknowns, two equations. Do. No hit. How about take a look at the first equation? If we take a look at the first equation, what do we have? Oh no. Okay. If you input the xyz into the first equation, you have focal length, you have xyz, you have the equation of all those EOPs, right? And that's it. And that doesn't mean anything. That means there's one unknown, which is time. Which is time, right? The second, if you directly take a look at the second equation, it has two unknowns. It has the y and it has the time. But the first equation, it only has time. So the reprojection is performed by first go to the first equation and get the time. And after you get the time, which indicates the y, it indicates the x coordinates, because the time indicates the x coordinates, right? Because the flight direction is the x, is the x-axis. So if you know what is the time that you are taking, what is taking, is that row? What is the time that you are taking the row? Then you should know where is the x coordinate. And with the time, then you can use the time and also the x, y, z to the second equation. So you have all the EOP, you have the focal length, you have the x, y, z. So you have everything on the right-hand side of the equation. The only unknown is y. So you can solve the y. So it becomes a two-step process. First, solve the time by using the first equation, then solve the y by using the second equation. Okay. you don't need to really like write down or take the note of the this equation because it's pretty long and it's on the slides, so you don't really need to do that. But if you want to do it, of course you can do it. Okay, so originally this was a later discussion, but because of the time, we don't have the time to talk about other things. So let's talk about this. Earlier, we mentioned that traditionally, you can get the EOP from the satellite company when you buy the image. And for example, this will be the information that you get. You get some control point for the EOP, and then so that you can derive the coefficient, the 18 coefficients for that. And then with that, of course, you can get, you can calculate the x and y coordinates. So which means that the imaging geometry was described by using this coordinate condition equation that in the old time, you can say. But however, nowadays, most of the satellite company, they don't want to release the EOP of their satellite. They don't want to do that. And one thing is they don't want to do it. And the second thing is that the users actually, they also don't want to get this type of information because there's a much easier solution to describe the imaging geometry between the satellite image and also the object space coordinates. There's a much easier way to do it, much easier mathematical function to do that. So in this case, that function is called rational function model, RFM. In Chinese, we will call it let's go rational function model, RFM. So this is the, so what exactly is RFM? RFM is, as you can see, like the general function format is like this. You have the x, y as the image coordinates, similar to the coordinate condition equation is similar. So you have the image coordinates over here on the left-hand side of the equation. For the right-hand side, you have four polynomial functions. You have four polynomial functions. And you have here I indicate that with the PC, PD, PE, PF. So 4 different polynomial functions. And for each of them, their format is like this. So I use PA. A can be replaced by CEEF. So which means that these four functions, their formats are the same. So this is the function of x, y, z, also similar to the coordinate condition equation. If you know the EOP already, then the only variable that you have is the x, y, z, the object space coordinates. So the format of that is you have the coefficients a1 plus a2x, a plus a3y plus a4z, and so on and so forth. Okay, as you can see, it's a polynomial function with the third order polynomial function. Of course, you can so you may ask the question, say why is like that? Why is like that? It can be generalized. It can be also simplified as a second order polynomial function. But however, usually we will use the third order polynomial function. Usually, so it's kind of more like, and you can use a higher label. But however, you need to derive the coefficient by yourself. The satellite complement in the standard way that's usually performed is this format, the third order polynomial function. And those coefficients, a1 to a20, for one polynomial function. As you can see, for one polynomial function, we have 4 polynomial functions. And one polynomial function will have 20 coefficients. We'll have 20 coefficients. And those coefficients, and so in total, we have 80 coefficients. Right? In total, we have 80 coefficients. Right? So we have 20, right? A1 to A20. So in total, we have 80 polynomial coefficients. And those polynomial coefficients has a specific term, which is called rational polynomial coefficients, right? And or in short called RPC. So RPC, they are the coefficients for the RFM, right? From time to time, you will hear people say, "Oh, what's your RPC? Where you can get RPC?" And RPC is the coefficients for the RFM. Okay. So what I'm trying to say is that right now, when you buy a satellite image from a satellite company, and they're in the metadata of the image, they will give you, for example, the XML format data, or maybe in other formats data. But however, inside it, you will see there are 80 coefficients. There will be 80 coefficients, and those 80 coefficients are for the RFM, right, to construct or to build the imaging geometry between the satellite image and object space coordinates. And you may not notice that because you never has the chance, and there's no requirement for you to open the header of to open the metadata of the image. That's because you guys are lucky, because most of the existing software, they have the, you can say, parser to parse those headers, to parse those metadata automatically when you import the satellite to the software, and it can directly read the coefficients and directly help you to construct the imaging geometry for you. Okay, but if you are doing the kind of a low level, no, not low level. If you are doing the photogrammetry work, and if you want to discuss, for example, image matching and those things, and then maybe you need to write your own program to process the satellite images. And in that case, you need to parse those coefficients by yourself. You need to parse it by yourself. So what I'm trying to say is that, as you can see, satellite companies, they will give you those 80 RPCs. Then in this case, for these 4 polynomial functions, you have everything beside the x, y, z, which are the object space coordinates. So if you have the object space